This is a reminder that you should feel free to take as much time as you need to write all of the notes down and think about them. Pause the video at your own pace.
What is up, my people? Are you ready for some math madness? Here we go. This is section 4.1, day 2 on quadratic functions. So we've got a formula for the vertex, and it looks like this. And if you want to find where the vertex is, all you have to do, if from this function, you get the a value, b, c value, just like in the quadratic formula, and you figure out what negative b over 2a is, and that's going to be your axis of symmetry. X equals negative b over 2a. Notice it has nothing to do with c, everything to do with b and a. Negative b over 2a. Anyway, that's the axis of symmetry, and then that's also the x value of the vertex. You can take that value and plug it into the function to get the y value of the vertex here. If you want to know where the x-intercepts are, you can solve the quadratic formula and you'll get two answers, and the answer 1 is here, comma 0, and the answer 2, comma 0 is over here. In general, that's how you can find these 3 points and this axis for any parabola that represents any function, any quadratic function. And so here it is. So let's do that. Here's some examples. Here's a function. F of x equals negative x squared plus 14x minus 47. And if the vertex is found with negative b over 2a, then that would be negative 14 over 2 times negative 1. Remember, there's an invisible negative 1 right here. Simplify that, you get 7. And plug 7 into the function, into the whole function, 7 here and 7 here. You calculate the whole thing, you get 2 as an output. So the vertex is at 7, comma 2. Now, because the a value is negative 1, we know it's going to be a u instead of an n. It's going to open downward, and then the vertex itself is going to be a maximum. That maximum value is going to occur at 2, where the vertex is. 2 is where the vertex is, so it's a maximum of 2. The range of the entire function, therefore, is from negative infinity up to 2. And increasing or decreasing? Well, it's increasing from negative infinity to 7. Remember, that's where the vertex is. And then it's decreasing again from 7 down to infinity. These are x values. These are not points. With all these x values, negative infinity up to 7, then it is an increasing function. Remember, it's a u. So that's the left part of the u. It's an n. So it's opening up downward. This is representing the left part of the n, and this is representing the right part of the n, where it's decreasing. I have a picture of this somewhere. Yeah, here it is. Increasing, decreasing. And it stops increasing and starts decreasing at 7. Notice that increasing and decreasing intervals are always represented with parentheses. Usually represented with parentheses. Discriminant. If you find the b squared minus 4ac, that would be b squared minus 4ac. That equals 8. And the 8 is greater than 0, so the discriminant predicts that when you solve the quadratic formula, x equals negative b plus or minus the square root of b squared over 4ac all over 2a, then you will get 8 inside the square root. And if you get 8 inside the square root, that means you're going to have 2. It's going to be positive. The square root will evaluate to 2 positive numbers. The whole quadratic formula will evaluate to 2 positive numbers, and therefore you get 0. It's greater than 0. You'll get 2 real answers and 2 real intercepts of the x-axis, as you can see here. And here they are. When you actually completely do the quadratic formula, this is what you get here, comma 0, and this, comma 0. You notice plus and minus. And these are going to be the x-intercepts. They're also known as zeros or roots. You can see here they are in the picture. 1, 2. Let's do the same thing with g of x. So here's the function. A is 1, B is 10, C is negative 10. To find the vertex, you can do negative b over 2a. Negative b over 2a is equal to negative 5. That's going to be where the axis of symmetry is. X equals negative 5. Plug it into the formula for the function. You get g of negative 5, and as an output, it's negative 45. So that means the vertex is all the way down here at negative 45. Because the a value is positive, we know that it's going to be an upward facing u, and therefore the vertex is going to be the minimum point. It's going to be a minimum, so the entire function has a minimum of negative 45. I'll let you do the range. It goes from the y values, the outputs, go from what all the way up to infinity as a range. Is it increasing or decreasing? Well, it's decreasing from negative infinity. For all these x values, it's decreasing from negative infinity all the way up to negative 5. And then it is increasing from negative 5 up to positive infinity. The discriminant, well, if you were going to do all this stuff inside the square root of the quadratic formula, that would be b squared minus 4ac. That's 180. And because it's positive, greater than 0, we know that we're going to have two real roots. The quadratic formula will yield two real roots. And here they are. Once you do the whole thing, it's negative 5 plus 3 square roots of 5, comma 0, and negative 5 minus 3 square roots of 5, 0. They're the two roots, and they're decimal equivalents. In general, what you can say about the discriminant is that it's b squared minus 4ac, and if it's greater than 0, it's got two real roots. It would look like this, two x-intercepts. If b squared minus 4ac is equal to 0, then there's exactly one real root. It looks like this. It's just barely tangent right here to the x-axis. And if it's less than 0, then you're going to get an imaginary number somehow, and it would be two complex roots, which would look like this: 0 intercepts, non-real roots. They don't show up on a real graph on the real x-axis. So let's do some word problems. Here, what we're going to do is we're going to be maximizing different things. Maximizing area, for example. We're finding the maximum height. And you're not going to be able to find, the answer is not going to be 3 or 10 or whatever. Like, you can't just solve an equation. What you're going to have to do is you're going to have to find, you're going to set up some equations, write a function for your unknown with lots of variables, and then use the other information to turn it into a function with just one variable. And then the answer is going to be the highest or lowest part of that function, the maximum or minimum. And so the answer is going to be a location on the graph that is the maximum or the minimum. So let's take a look at this. Maximizing area. Landscaper has enough bricks to enclose, as you can see right here, to enclose a rectangular flower box below the picture window of the Jacobson's house with 12 feet of brick wall. If the house forms one side of the rectangle, what is the maximum area that the landscaper can enclose? What dimensions of the flower box will yield this area? So basically what we're going to do, it's really good to draw a picture. We've got this area inside that we want to maximize, find the maximum area. If you set this up wrong, you're going to get maybe something that's too skinny and not a whole lot of area, or too tall and not a whole lot of area. But if you do there's a sweet spot in the middle that's going to give you a whole lot of flower box area. And this one side here is the house, so we don't need to actually put any brick here, despite what the picture might look like. You only have 3 sides of brick. And this is going to total 12. You're going to have one width and another length, and that's going to equal 12 feet, as you can see right here. Then the overarching equation for the area of a rectangle, if you have to maximize the area, we have to figure out how to calculate the area. You'll calculate the area by multiplying length times width. So these are the equations that you know, and you can even rewrite width plus length equals 12. You can rewrite length equals, rewrite this to solve for L, 12 minus 2w. I'll show you why we did that in a second. The unknowns are the actual length and the actual width and the actual maximum of the area. Anyway, if we want to maximize this, we need to turn it into just a function of one variable. This is no good to have two different variables, length and width. We just want one, because then we can graph it. So we're going to use this other fact to figure out what L is equal to in terms of W. And then you're going to say, well, area is length times width. That's going to be here no longer length, but what length is equal to. Length is equal to 12 minus 2w, and there it is, 12 minus 2w times w, and then when you distribute the w, you get area equals 12 width minus 2w squared. All of a sudden, this is a quadratic formula that we could, plug into Desmos, and we could find the vertex and all that stuff. So, once you have a quadratic equation, this is what it looks like. So the axis of symmetry will be at negative b over 2a, which is at 3 feet. That's what negative b over 2a calculate out to. And if you plug 3 back into the area function, you can figure out what the area actually is. It's 18 feet squared. That's 12 times 3 minus 2 times 3 squared. Here's the vertex of the graph. 3, 18. At any other x values, or in our case, in any other w values, you're going to have something less than 18 feet squared. But if you just make w equal to 3, then you'll have the maximum area that you could have. Here it is in the graph. And you can see this is what I typed into Desmos to produce the graph. But even if you didn't have the graph, you'd know that the width, the vertex of the width is going to occur on the axis of symmetry where negative b over 2a, that's 3 feet. Anyway, the width is 3, and if you plug it back into the length equation, you get length is equal to 12 minus 2 times 3, which is 6. 3 feet by 6 feet is 18 feet squared, and that's as large as this flower box can go. The height of a rocket. One model rocket is launched with an initial velocity of 100 feet per second from the top of a hill that is 20 feet high. Its height in feet t seconds after it's been launched is given by the equation s equals negative 16t squared plus 100t plus 20. This 20 came from the starting height at the top of a hill. The 100 comes from the initial velocity, the starting velocity of 100 feet per second. And the negative 16, comes from gravity, the fact that gravity is pulling down at a strength of 16. Determine the time at which the rocket reaches its maximum height and find the maximum height. Well, here are the a, b, and c values. In order to find the vertex, or the axis of symmetry, we do negative b over 2a, and that's negative 100 over 2a, 2 times negative 16, which turns out to be 3.125 seconds. 3.125 seconds is right here. This is where the axis of symmetry is. If you plug 3.125 back into the function, if it's the input, 3.125, then you get as an output 176.25 feet. And at this point, I just want to let you know that John Adams is the president for this particular video. That's your audio check president. He's at 160, maybe he's at the top of this hill. Maybe he's launching this rocket and seeing a height of 176.25 feet. In any case, there are the answers. Here's the time, and here's the height. Time, height. I'd like you to start on the assignment 4A2, copy the problem list, and do the first problem, and I will see you in class.